Hi everyone, in the previous video I was chatting about linear independence and I gave you an example of two vectors that were linearly dependent. In this video, spoiler alert, I will give you an example of two vectors that are actually linearly independent and how you can verify that. The vectors that we're talking about today are A equals 1, 1 and B equals 2, 3. Straight away you can see that it's not possible to make one using a linear combination of the other. Okay, it's a lot harder to see this when you have more than two vectors though. So here it's a really nice and simple case, but I want to show you how you can work it out when it's a not so simple case. Remember, the idea behind linear independence was we want this 0 vector, 0, 0, to be made up of a linear combination of the vectors in our set here. So here that's the vectors A and B. So we want to try and make 0, 0 out of C1A plus C2B. That means we want 0, 0 to be equal to C1 for 1C1 plus 2C2 and C1 plus 3C2. And what we want to show for linear independence is that there's no way to get this working unless we make both C1 and C2 0. So let's have a look at the first cell in green. So we need to satisfy this equation. Cell 1, we have that 0 equals C1 plus 2C2. Let's rearrange so that we get one constant as, Okay, so we've got C1 equals minus 2C2, just by rearranging there. And we're done for that one. Let's circle or wrap around this one. That's something that we know has to be true if we're going to get that first cell to equal to 0. Let's have a look at cell 2. For cell 2, let's work out what needs to be true to get that 0. Here we have 0 equals C1 plus 3C2. We'll rearrange and we get C1 equals minus 3C2. And there we're done. Okay, so to be able to satisfy this 0, 0 equals to our linear combination of A and B, we need to make sure that C1 equals minus 2C2 and C1 equals minus 3C2. Straight away we can see there's a little bit of an issue here because we're looking at minus 2C2 and minus 3C2. But let's have a look. Because in each case C1 has to be exactly the same thing, that means we can take the right hand side of each of these equations, make them equal each other and see what happens. So minus 2C2 from the right hand side of that green equation has to equal minus 3C2 from the right-hand side of the red equation. Okay, so to be able to work out what this is, let's add 3C2 to both sides. When we do that, we've got minus 2C2 plus 3C2 equals minus 3C2 plus 3C2. Minus 2C2 plus 3C2, we get 1C2, or just C2. And then this minus 3C2 plus 3C2, we get 0. Oh, okay. So because C2 equals 0, that means that C1 equals, and we can choose either one here. So we can choose the green equation or the red equation. But C1 equals minus 3C2 from that red equation equals minus 3 times 0 equals 0. Now, because we have C2 equals 0 and C3 equals 0 as our only solution, we can say, therefore, the vectors A and B are linearly independent, because there was no way to make that linear combination equal the 0 vector back up here without having both C1 and C2 equal to 0. All right, we're done.